Hello everyone, welcome to the lecture number 41 of this NPTEL lecture series on charging infrastructure, where we will be continuing our discussion on small signal modeling of PSFB converter. And in the last lecture we have derived or we have arrived to the equivalent circuit for a small signal model of PSFB converter, where we have seen we have the input voltage and then the transformer having the turns ratio 1:D, and we have the one constant voltage source, then we have control voltage source, and then we have this current source, then followed by control current source L, C and RL, and here we have our IL current which is going like this over here. So now let us see how we can then derive our small signal model, or from this circuit diagram how we can then arrive to different transfer functions which we have to look for. So let us first define this point as A and B point. Since we are trying to find out GVD of S, which is variation of output voltage whenever there is a variation in the duty ratio at the place where our Vin, change in the Vin is equals to 0, that means Vin is not gonna change. So that is actually, we can then say, since my Vin is not gonna change, what I can do is my duty ratio dV is actually equal to 0. That is when from this circuit we can then write the VAB, the change in the VAB we can write from here, looking from this thing, is nothing but equal to, we can just say NV in, we can just say from here in this particular circuit, if we take if we just take the KVL in this particular loop, if we take a KVL, then it will be VAB, small value of VAB is nothing but equal to dNV in plus dV is 0, so it is di tilde NV in voltage. So we can write down that, and that we can just take out NV in is equals to d tilde di tilde, we can just write VAB, small signal, the small value VAB. Let us define this as equation number 1, and we can take the S domain in that, we can say NV in ds and di of S, we can write that. Also we can write from time domain to this domain we can go, and then we will define our one transfer function, let's say H naught of S, we will define to be equal to V naught of S divided by VAB of S, we can say, and that we can just write my V naught of S to be equal to H naught, of S and VAB of S, and that I can just write from equation 1 and V naught of S to be equal to H naught of S and V in D of S plus di of S, that we can write here. Now let us define this expression to be equation number 2, and then after that let us try to further find out some more expressions from there. If we look into this thing, we can define, looking at the terminal AB, we can then define the input impedance. So we can say input impedance, and that input impedance will be looking from this terminal, we can just say input impedance from terminal A and B, we can say Z input AB, we can write, obviously this we will write in the S domain, which is SL, we can say SL in obviously in the Z in, we can say in S domain, we can say in S domain or in frequency domain we can write. So this inductor, the in frequency domain the impedance will be SL, and this will be 1 by SC, that 1 by SC is coming in parallel to RL, so we can say SL, and this is SC times RL divided by 1 by SC plus RL. And then if we do this thing, we can just write Zin or input impedance looking at AB terminal is to be equal to S square, because this will go S square, this will go over there, is LCRL plus we will get SL, because from this term SC will get cancel out, plus we will have RL divided by we have 1 plus SCRL. This is what we will get as Z input impedance looking at from the terminal AB. Let us define this term to be equation number 3. Now what we can do is we can then define our V naught of S. If we see the V naught of S is nothing but we can just say my VAB of S divided by this input impedance looking from the VAB terminal in this direction. So this is the VAB by S divided by this thing will be nothing but the current, and this current will be actually divided into the branch 1 by SC and RL, and that will be multiplied with RL. So we can just say 1 by SC divided by 1 by SC plus RL into my term RL, where we can just say that this term if we will get it by the current division between 1 by SC and RL impedance, and this RL multiplication with this current which is flowing through the RL multiplied by RL, when we do we will get the required voltage. We can say this is due to the current division, and we can say this is current flowing through RL, and this multiplied by RL will be nothing but equal to your V naught. Now let us try to see from equation number 2 how we can correlate these two terminologies together. So then what we can do is we can then write V naught of S divided by VAB of S, Z in AB of S from equation number 3 we write. So this will be nothing but will be equal to S square LC RL plus SL plus RL. This will be 1 plus SC RL coming over the top, multiplied, because this I have taken it to the division on the left hand side. This one, this SC will go over there, and this SC and SC will get cancel out. So this here we will get RL by 1 plus SC RL we will get over here. And if we look very carefully, this and this term will get cancel out, and this if we see from our expression, if we see from our definition the H naught of S, we can say this term is nothing but H naught of S is nothing but equal to 1 by, we can say this RL also we can take it below, we can say S square LC plus S L by RL plus 1. This let us define at equation number 4. So from the input impedance term we got the H naught S, which is nothing but equal to V naught of S divided by VAB of S. Now let us go ahead and then try to find our GVD term, which is V naught by D term. So we know that our DI is nothing but to be equal to minus T by Ts by 2 if you recall our previous discussion, and then from here we can just write minus 4N L leakage times F switching divided by V in, and that is IL bar, we can say DI term, we can just write that term. So then we can just define the R equivalent to be 4N square L leakage FSW. We let us define this term, and this we can just from this equation we can just write down, let's say this was 4, this is 5, and this is 6. From 5 and 6 we can just say that this particular term will be equal to this thing, and this we can just write IL tilde to be equal to NV in, because n we have to divide and n square will become here over here, and this will be divided by R equivalent times di we will get. And we already know our Z in, if we recall our from equation number 3, Z in AB of S to be equal to S square LC RL plus SL plus RL divided by 1 plus SC RL. Okay, this we can achieve from equation number 3. Now, if we look very carefully, this IL is going from the VAB, this IL. So, we can just write our IL term to be IL of S, we can just write to be equal to, we can just say VAB tilde by S divided by my Z in AB of S, we can just write that. Similarly, this particular expression we can also write IL of S to be equal to NV in by R equivalent times DI of S. This, let us say, this define is as to be equation number 7. Now then we can also write our this particular term which we got over here, we can just write from equation 1, we can also write our IL of S to be equal to N VAB, we see equation number 1 to be NV in D of S, since we are writing in terms of S domain, so we can say DI of S. Let's just take this entire equation, this equation to be 1. If we just say that this is equation number 1, so we can just write IL to be this one divided by, we can just say it is nothing but equal to our Z in, looking at from AB input impedance into S. This we got, we have missed this minus negative sign over here, and let us define this term to be equation number 8, and from equation 7 and 8 we can write a simplicity, in a simpler manner we can just write that we have minus N V in DI of S divided by R equivalent to be equal to N V in D of S DI of S, and if we see divided by Z in, looking at from AB terminal of S. This, when we rearrange this particular term, we will get a term DI of S to be equal to, we can just write in terms that we get minus D of S divided by D tilde of S I missed here. Here also D tilde of S will be there, because from equation 1 if we see D tilde is there, this I missed over there. This is D tilde of S, I mean if we rearrange this one, it is minus D tilde of S divided by 1 plus Z in, looking at AB terminal, divided by R equivalent. This entire term, let us define this term to be equation number 9. So what we got is, we have got DI tilde to be equal to minus D tilde by 1 plus Z in ABS by R equivalent, that will be we have defined this as a equation number 9. Now if we take the equation number, let us define our equation number from equation number 2, we can just say that from equation number 2 we can say that our V naught of S is nothing but H naught of S times NV in D of S plus DI of S and this we can put this di of s from equation 9. From equation 9 we can just put h naught of s and v in d of s minus d of s 1 plus z in abs by r equivalent. This entire expression we got. Now when we rearrange this particular thing, what we gonna get is v naught of s is to be equal to h naught of s and v in. This will go at the top, this ds will get cancelled out, and then finally what you are gonna get is we are gonna get as z in ab of s divided by z in ab s, looking at from ab terminal, input terminal looking at ab terminal plus r equivalent, and this we are gonna get this particular term multiplied by d of s. Now this particular expression we can then write v naught of s d of s, which is nothing but our zvd of s. This from our previous equation we can just write h naught of s and v in the bracket. We have input impedance looking from the AB terminal divided by input impedance looking from the AB terminal plus R equivalent. We got this term. Now this particular term Z in we can put it from equation number 3, h naught of s from equation number 4, and then let us try to find out what is GVD. So GVD of s is nothing but h naught of s. Let us try to put h naught of s 1 by s square LC plus SL by RL plus 1 times n times V in the bracket my Z in, this thing Z in looking from ABC. So S square LC RL plus SL plus RL divided by 1 plus SC RL we got over here, slightly bigger, divided by let SC S square LC RL plus SL plus RL 1 plus SC RL plus R equivalent we got. Now let us try to resolve this one. This will become RL goes to the top, S square LC RL plus SL plus RL into N into V in. Now this SC this will get cancelled out, and finally in the top is C S square LC RL SL plus RL divided by what we have is we have S square LC RL plus SL plus, if we just go over there it is L plus C RL R equivalent plus R equivalent we have got. Now if we see this particular and this to this thing get cancel out, so if we try to see, this will get cancelled out, this will get cancelled out, and finally what we gonna get is NV in at the top, RL we can take it at the bottom, S square LC plus S L by RL plus RL get cancelled plus C R equivalent we have got plus This is R equivalent by RL. Now this is my ZVD what we got, where RL we know my load resistance, L is the inductance, output inductance we are putting, C is the capacitance we are putting, R equivalent, if we can see what is R equivalent. R equivalent, we have already defined R equivalent to be 4 N square L leakage times FSW. Now this is actually your, we can say that this is the transfer function of PSFB, which captures the output voltage dynamics whenever there is a change in the input or change in the input duty ratio, or you can say change in the duty ratio. Now if you recall, this is the case when this is, this is at the case when my V in tilde is actually equal to 0. Here we have taken one consideration, that my V in tilde is actually equal to 0. So this is what we will get the GVD closed loop transfer function, and this we will use it to find out the controller parameters when we are defining the closed loop transfer function. So let us define our, how our closed loop system will look like while we are actually trying to find out how to, find out the controller parameters. So our closed loop system will look like, we have the V0 reference, output reference we are keeping, we are having V0 feedback we are getting, which we are getting it from the, sensor. Here we will put some controller, it could be PI or it could be P, it could be PID, it could be type 2, it could be another higher end controllers we have. Then here we have K, again K, which is actually being sent to the modulator block, which actually defines the phase shift of S1, S2, S3, S4 switches. So whenever there is a change in the, duty ratio here, there will be change in the phase shifts, and that will actually changes the output voltage. So here we captures our GVD of S, and that will be the actual output voltage which will be there, which will be actually be sending from the sensor transfer function going back to the feedback. So here we can define S, here we can define V naught of reference. Now this is the transfer function of output voltage sensor. We have this, we have already derived K. The K is the gain, which is defined to be K to be equal to control voltage, or you can say maximum control voltage Vc, you can say, divided by the maximum output voltage. So since if we see in this one, so this will be in the microcontroller, so there will be gain block which actually step down the real output voltage into the voltage level to that of control voltage. So that is why this gain block has been implemented. This is in the microcontroller side, this is the actual converter side. So using that, we can then define our controller parameters by, so the guidelines for controller parameters to be is, we have already discussed in detail while we are doing the boost PFC. Here we can say the guideline, first guideline will always be provide high gain at the frequency at which provide the high gain at the frequency which the closed loop system need to track down. So since we have reference which is a DC value, so we must provide a very high gain at s equal to 0. So in our case, the high gain needs to be provided at s equal to 0. That means by putting a pi which introduce a pole at s equal to 0 will serve the purpose. Then the next thing which we wanted to have is we must have sufficient phase margin, which you can get by putting the open loop transfer function. So here we have open loop transfer function to be nothing but my controller transfer function. Let's say my controller transfer function is C of s. So we can say that it is C of s times k times GVD of s times h of s. So this we can define the open loop transfer function, and for this open loop transfer function, when you plot the Bode plot, we must ensure a sufficient phase margin for open loop transfer function, which is OLTFS, which let us define this as equation number 10. PM for open loop transfer function. This can be done using Bode plots. So we can provide a very high gain at the frequency which the closed loop control need to track down. In our case, since we are trying to regulate the output voltage, and output voltage is a DC quantity, so we need a very high gain at s equal to 0, which can be done by just putting a PI controller, defining a proper KPKI, such that we have the sufficient phase margin for this open loop transfer function, which also includes this controller transfer function. And here if we look very carefully, this one, it is better to have PM greater than 35 degrees. Going from 35 degrees to 90 degrees, it is better to have that. And then you can also provide sufficient bandwidth, or you can say zero crossing of your open loop transfer function, such that the controller does not get overburdened. At the same time, you will be in a position to track down the frequency of concern, such that the controller does not get overburdened and closed loop system is able to track down frequency of concern, or frequency of concern frequency, track down the concern reference frequency. So this is what, using these three guidelines, one can easily design the controller parameters, using different tools which are there, one can do that. So if we look the overall system, it will have, if we see our this converter, this is having our switches, and this is our transformer. So, if this is our converter and this is the output voltage which we are trying to control. So, what we will do is inside the microcontroller use some different color, so that you will understand what is happening in the controller. Inside the controller we have this V0 reference which will be set inside the controller. This will be my V0 feedback which will be coming. This is my controller GC of S. Then output of this controller will be actually going to the, if we see, is going to the gain block K, and this gain block K will be, then we can limit our duty ratio. Let us say 0 to maximum we can go up to 0.95 example. I mean, we can also take 0.9, and this is then going to the modulator block. This is a D value which is coming, modulator block. Now, in the modulator block, this D, the duty ratio is there, is will now get converted into phase shifted. You can just write gate signal for S1, gate signal for S2, gate signal for S3, and gate signal for S4, and these are actually going to the gate of this S1, S2, S3, S4 switches. Now, in the modulator block is like modulator block converts the duty ratio to phase shifted signals. I mean, correspond to that duty ratio, it will give the appropriate phase shift angle. This you can easily define the relationship which we have seen in previous lectures, and you can define how from the duty ratio information we can give it the delta value. Then what to do is, on the other side you are actually sensing the voltage V0, and you are sending it to your inside your microcontroller through the sensor. So, this sensor, we have defined this sensor block. This is transfer function of sensor. Just define transfer function block of sensor. And then what will happen is that after this gets converted into the low voltage signal which is going into the microcontroller, and which is then feed get controlled over here. So, this part what is there in given in the blue color is actually there inside the microcontroller, while the red part is the actual circuit and the sensor which we have in our circuit. So, this is how one can do the closed loop control to actually find out, or to actually do the regulation at the output voltage. And here, to find out the parameters of controller, we have done the small signal model and found the transfer function of ZVD, which captures the dynamics of output voltage variation whenever there is a change in the duty ratio, and for using that thing we can formulate our controller parameters, and that we can put it in our system, so that we can do the closed loop control. Now, this is the simplest closed loop control for the PSFB we have demonstrated, where we are just trying to regulate the output voltage irrespective of any other controlling action. Many a times researchers have also done the peak current mode control of the transformer current. Now, the benefit which we get from doing the peak current mode control is that, let us say, whenever the diagonal switches, two of the diagonal switches, which is S1 and S4, and S2 and S3, whenever S1 and S4 turns on, there is also a finite voltage drop which takes place across the S1 and S4, S2 and S3. So, these voltages which are dropped across the switches will be different, and because of that there is some small value of voltage difference will be there between the positive voltage and the negative voltage which will be applied across A and B point, and this voltage will lead to the flux to grow either in positive direction or in negative direction, which will actually lead to the core to go saturation after certain cycle of operation or after certain period of operation. So that's why people do the peak current mode control, which could be integrated with the output voltage control, the inner dual loop, which can be integrated in the inner dual loop, which actually helps you to balance out or to keep the transformer current to be within the value which actually lead to the saturation of the transformer. So that can also be incorporated. However, here we have demonstrated the simple single loop closed loop function to actually regulate the output voltage of PSFB. So with this we will conclude our discussions on the phase shifted full bridge, where we have seen how this PSFB actually works in different operating modes. Then we understood what are the conditions to achieve the soft switching of lagging lag and leading lag and how we can do that. And then after that we have gone through and study how, because of the introduction of that ZVS phenomenon, how we get the loss in the duty ratio, and because of that we will have additional dynamics in our system which we have incorporated in DI and DV functions. And then from there we derived the small signal model using the buck converter model. We have derived the small signal model, and then we have extended it to our phase shift full bridge converter, and from there we have come to the GVD transfer function, and then we have defined how we can do the simplest closed loop control to regulate the output voltage. However, one must also incorporate the peak current mode control along with this output voltage control in order to ensure the flux walking of the core does not take place. That means the flux should not go either in positive or in the negative direction, because it will lead to the saturation of the core of this high frequency transformer, and which is one of the critical aspect in order to ensure the safe operation of this converter. In the next class we will do a brief discussion on dual active bridge and its modulation schemes. Thank you very much for patiently listening to this lecture. We will meet in the next lecture.